Alrighty. Hello everyone. Good morning or good afternoon, wherever you are. Welcome to the fifth video or fifth webinar in our session on the electric vehicle integration project. Today we'll be hearing from Will and Nando on the results on the control of home charging and the use and time of use tariffs. So this is, as I said, the fifth session in our video. Just a quick bit of housekeeping and some introductions, noting that many of you have been with us throughout the whole series, so this is familiar, but we do have 638 people registered today, so there's a few new faces, so we'll just give them a bit of background and then quickly jump into it. So first off, we are recording this webinar, and you should be able to see at the bottom that there's also an automatic transcript going on, so that's to help us access both live and later if you need to, and all of the other videos are available. As we come together as an online community, I'd also like to acknowledge the traditional custodians of the lands and waters that we are meeting on today. I'm here in Lutruwita in Tasmania, but you know, there's traditional custodians of lands all across this amazing country that we live in, and I acknowledge their elders past, present and emerging, and any Aboriginal or Torres Strait Islander people that are joining us today, and acknowledge your continuing contributions to our culture and our community. So our webinar today, as I said, fifth in the series, building on the project work that's been going on for almost 2 years now. So we look forward to hearing from Will and Nando on that. As some background, the API where I work, our focus is on sharing knowledge from innovation projects and other areas so that we can build the workforce for the future. And I just want to acknowledge our member organisations that support us in the work that we're doing, which makes it possible for us to do things like this. This project is part of what's called the Australian Strategic Technology Projects, cooperation between the Australian Power Institute and Energy Networks Australia. And the goal of that is to link universities with industry-based problems. And we're really lucky that these projects bring in great teams like the Melbourne University team, but also other partners like C4Net. And together we work on challenging problems that benefit across the sector. If you're interested in the previous webinars, they're available in a number of channels, but one of them is through the API's YouTube channel, and this video will appear up there as well. So you can find that by just having a look for Australian Power Institute in YouTube, and it's in a playlist. If you're also interested in some of the other reports and the slides from our webinars, they're available through C4Net's project page, and you can find that on C4Net's website. The details are there, and our Melbourne Uni team will also share some of the info that they have and where you can find their extra resources. So now I'd like to just throw to Dawson Tan from Energy Networks Australia, who will tell you a bit about ENA. So over to you, Dawson.
Thank you very much, David. I'd also like to join you in offering my respects to the Indigenous peoples of Australia, and just note that I'm speaking to you from Melbourne in the lands of the Wurundjeri people of the Kulin Nation. Good afternoon. My name is Dawson Tan. I am head of distribution networks at Energy Networks Australia. We are the peak industry body representing electricity transmission, distribution, and gas distribution companies in Australia. I'd like to thank our funding partner, James Seymour, another panelist who you'll see at C4Net, who have been a brilliant project partner and have recognized that our mutual interest in helping to shed light on some of the many opportunities of the energy transition. My thanks also, obviously, to the University of Melbourne and the Australian Power Institute for their support in delivering these important insights to not only us, but also to you. Electric vehicles are well and truly inevitable, and if there were any doubts about that before the recent federal election, there certainly shouldn't be any now. Speaking on behalf of my members, we have a keen interest in minimizing disruption to customers, maximizing the opportunities that the transition represents, and continuing to provide safe, reliable, and economically efficient power. With that, I'll get out of the way for much more interesting results. Thank you very much, David.
Thanks, Dawson. So over to Will and Nando, the dream team, to share part 5 of your project update. Thanks, gentlemen.
Excellent. Let me share my screen. Am I sharing the right screen? Now presentation mode.
Yeah, you're sharing. Yeah, there you go. Perfect.
Fantastic, fantastic. Well, good afternoon, everyone. Thanks for joining us, and thanks for the introductions, and thanks, of course, again, to the API, ENA, and C4Net for funding this project. So today is perhaps the last webinar that will really look at the different technical challenges and opportunities that we have once we start having lots of electric vehicles connected to our distribution networks. So we are going to discuss, of course, the management of electric vehicles. Today, we're going to discuss some opportunities by managing directly the chargers. And also, we are going to look at opportunities of using time of use tariff. Of course, for the benefit of everyone and the audience in general, we are going to start with the basics and also what has been done before, so you can understand what are the benefits of some solutions with respect to the non-solution kind of scenario. So we are going to go through this kind of in different how to explain this. We're going to present. I'm going to present some of the different aspects, of the techniques, the methodologies, the high-level aspects of that, and then we will be presenting the results. So we're going to be interacting a lot throughout the presentation. Do feel free to write your questions there on the chat or the Q&A, whatever you want. We will go through them at the end. There should be some time to go through them. So please do write your questions. Don't wait until the very end. All right, so let's start. So the outline today, let me just move this little, and there's live transcription there. Can I just, there you go, I'm closing it. All right, excellent. So the outline today, we are gonna go through just the context, of the project, the context of electric vehicles and the grid, super quick, a little bit of the modeling that really underpins everything that we have done. And it is very important to acknowledge that, because without that modeling, we wouldn't be presenting any results. We are gonna discuss the impacts of electric vehicles on the distribution networks. We have been very lucky to be able to model different distribution networks across Australia, particularly 3 states, and not just any networks that they consider that could actually benefit from this type of studies because they have special characteristics. Then we're going to get into really the important part of this presentation, which is the electric vehicle management and the time of use tariff for electric vehicles, and we'll conclude some recommendations. Now, I'm very happy to say that the report that is part of this part of the project has been released publicly. We will provide the links, etc. So you can go definitely in much more detail, and all the different results that we have that are extremely extensive. Actually, as a matter of fact, that's a large report. You will be able to go through that yourself. All right, so let's continue. So first, the project, as David was mentioning, this is the electric vehicle integration project. In short, we have another bigger name, but that doesn't matter. Right now, what we are presenting, we've been through different aspects of the project, but today what we are going to be discussing is the integration of electric vehicles using active management strategies. There's still another stage of the project, which is the techno-economic network and system integration aspects of electric vehicles, and then we will be finalizing the project in September. So this is not the final webinar. There's still more to come and more reports to come as well. The team at the university side, of course, we have a lot of support from the API, C4Net, and ENA, but from the university side, this is the team that has the techno-economics aspect that is being worked on right now, the customer aspects as well, transport, and right now, well, we are focusing on the distribution networks. Now, let's get into the context of electric vehicles and the grid. So, as Dorson was mentioning, well, this is certainly inevitable. And if we're going to see more incentives, let's say here in Australia, well, the predictions that AEMO was making recently in their integrated system planning report might come true. And right now, what I'm presenting here is just an average of those predictions that were done recently by AEMO and with data from CSIRO as well. So that's the link there that you can actually download it yourself. So we did an average of all the different scenarios, because as scenarios, different things can happen. But even if you average all the scenarios that AEMO put together, what you see here on the red line is electric vehicles, all right? This is considering 7 kilowatt charger that actually, well, is what we are gonna call here throughout the presentation a level 2 charger. So this is 32 amps, and with the voltage that we have at home, which is 230 volts, then well, we have 7.4 kilowatts. So the demand that we're gonna see, in megawatts, the moment we start seeing this uptake of electric vehicles, is going to be astonishing. And there are significant challenges, not only from the perspective of AIMO, as in where is the generation of electricity going to come from, to supply all this electricity and all the renewables that we might need as well, but also from the perspective of the poles and wires, the distribution companies, how are we going to handle this new demand? And the thing with electric vehicles that differently from what you can see from photovoltaics, the rooftop photovoltaics, that we know that we have a lot, is that the uptake will happen, which starts happening really significantly, will go fast, and will go so fast that if we don't make adequate decisions today, we are going to see problems, all right? And we don't want that. So we need to be very strategic with our decisions when it comes to the management of electric vehicles or the preparation of our grid, for the electric vehicle reality. All right, so what are these challenges that I'm talking about when it comes to distribution networks? Well, I mean, let's first understand the design principles of a low voltage network. So those are the poles and wires that you see on the street, connecting our houses, our shops, etc. So we consider, essentially a demand that is kind of a diversified peak demand per house. And based on that, we design, what is the size of the transformer that is more adequate, and, the corresponding wires, given distance, and all our assets and the voltages are okay, are within the limits. All of this, of course, depends on the diversity of the region, demographics, demand growth, etc., different factors. So for instance, in New South Wales, you might use values of around 6.6 kVA, per house, and that is because of air conditioning. However, in Victoria, despite that we use as well air conditioning, it's much less. And well, Tassie, for instance, they will use other values because as well of heating purposes. So these values are different across Australia, which also tells us we need to understand the different characteristics to really make some conclusions that are applicable to the different states and different regions, right? Now, the moment that we look at how we design our low voltage networks, it gives us an opportunity to understand that if we start putting, for instance, electric vehicles that are going to have a demand of 3 or 7 kilowatts, as I was mentioning earlier in the plot from AIMO, it means that we might have some space or not, depending on the particular network that we're talking about. So if the design was done, for instance, with 3 kilowatts or 3 kVA, per house in a region in Victoria, then suddenly every electric vehicle, will have 7 kilowatts. Well, if everyone charges at the same time, well, that's double the design values that were used. And that is worrying. However, perhaps, if people are not going to charge simultaneously, and then also you have a lot of space or headroom, if you want to call it like that, in New South Wales, then perhaps it's okay. So it all depends really on how you design those networks to then understand what are the potential challenges, for integrating electric vehicles. Now, the moment that we look at the electric vehicles, like we mentioned, we have 2 levels that we're going to use, throughout this presentation as well. Level 1 and level 2. It's also called mode 1 or mode 2. But in general, it's just 3.7 kilowatts and 7.4 kilowatts. Now, 7.4 is the one that internationally is actually being adopted much, much, much faster because, of course, people want to charge their vehicles much faster. Now, it's more expensive level 2 charger than a 3.7, and that, of course, can create some limitation for some people. The installation as well might be not that simple for certain type of premises, but still, that is the trend. Now, the moment that people come from work, from commuting, for whatever, and they come at night most of the time and then start charging, well, we can have a coincidence of demand that can be so big that can actually push our voltages down below the statutory limits, and we can actually perhaps jeopardize as well the integrity of our assets. So imagine, power flows, currents that are much bigger than what our conductors are designed for, or our transformers. So we need to be very, very careful with this. And it's not just the low voltage part of the networks, it's also the high voltage, 22 kV, the 11 kV, 33 kV voltages that we have. And also considering that Well, certain networks are designed, for urban areas where the density is much larger. We will have larger transformers. We will have many, many more houses. And well, of course, the impedances are not going to be necessarily that big with respect to the zones of station. But in rural areas, we're going to have much larger conductors, much larger impedances, lower density, but the smaller transformers, which is something that can actually cause problems as well, because with the smaller transformers, we can have problems much, much sooner. So all of this needs to be understood, because these problems can happen, the moment that we have widespread adoption of electric vehicles. So the first question is, how can we determine the hosting capacity of our networks? And well, that we kind of, answer this in some other reports and webinars, so you can go through that as well. We're going to present some of the results, but now is how can we increase the EV hosting capacity? And this is the purpose of this particular webinar and our final report as well, in terms of EV management. How much can we increase, and what are the recommendations from all these studies that we have done? All right, some definitions, because we're going to use certain words a lot here. When we talk about hosting capacity, particularly electric vehicle hosting capacity, we're talking about the maximum amount of electric vehicles that a given distribution network or part of it can host without negatively affecting its normal operation. Now, normal operation has different characteristics. Most of the time, we can refer to the voltages, within statutory limits, and asset utilization. So you don't want, the assets to be overloaded. But there are many other aspects that in reality need to be considered, like protection, harmonics, etc., etc. We are not considering that. That would be a much, much larger study. So we're just focusing on voltages and asset utilization. Now, when it comes to the number or the amount of electric vehicles, we are going to refer to one electric vehicle per house as the metric that we're going to use for penetration. So if we have 100 houses and we say 60% penetration, it means that 60% of those houses have one electric vehicle. Now, we know that some houses can have more than one electric vehicle, right? So it means that we can actually go beyond 100%, right? So bear that in mind. Now, let's get into the modeling. I mentioned that this was critical for everything that we're going to present later on, because of course, we need to run power flows. We need to understand the basics of how our networks, our physical assets, are going to behave the moment that we have much more load. Now, typically, distribution companies, not just in Australia, but around the world, they do have very good models, on the HV part. So these are the 11 kV, 20 kV, 33 kV networks. And that's great, of course, to have that models. They use it every day, for different planning and operation purposes. However, the low voltage part is the part that it is not really modeled in detail, just because of different historical reasons and some challenges that they have as well. So we needed to extend those models that we got from different companies, part of this project, and that was very important. So we could actually quantify what is happening at the connection point of these houses. Now, here it is a summary of the networks that we were using. So thanks to our colleagues in New South Wales, Tassie, and Victoria. So we ended up just modeling 6 high voltage networks, and we extended them to their corresponding what we call pseudo low voltage networks. So they are not the real low voltage networks, but they are pretty realistic and follow design principles that are used here in Australia. So therefore, it does give us but it is a way of quantifying the potential impacts at the connection point of the customers. And that's brilliant, because then you will be able to assess voltages as well as problems of the conductors that you might have in the low voltage networks. Now, of course, there are limitations, because the design principles that we use are the most modern ones. And of course, many of these areas might already have design principles of 10, 20 years ago, right? So there are some caveats there, but still it does allow us to do really detailed power flow analysis, 3-phase power flow analysis and balance. We use OpenDSS, which is an open source tool for these purposes. Now, another aspect of modeling is not just a network, as challenging as it can be, is also having adequate data. And that data I'm referring to is the data of the electric vehicles. So there is no, today, although there's a lot of work from the organizations such as C4Net and other companies are trying to gather data, but there's not a lot of publicly available data for electric vehicle charging profiles, or demand profiles. So what we did is we went to this project Electric Nation, and they have publicly available raw data of more than 700 electric vehicles. And this is a relatively recent project, that ran in 2017, 2018. And with this data, we started processing it so we can actually extract the statistics that they capture, from this real data. And with these statistics, we created our own profiles. Now, of course, this project is from the UK, and some of you might consider that, well, the UK is not necessarily the same as Australia. However, we did some checks with travel service for certain parts of Australia, and actually it was very close. It wasn't the same, sure, but it is applicable. So it is a pretty good starting point. Now, there are multiple steps. I'm not going to go through the details, of course, because there's a lot of details there, and there are reports and webinars that can actually give you more information, but this is just for completeness. Now, we end up with profiles that look like this. On the left, what you see is an individual profile of different electric vehicles. So you see those that actually have this square shape. That means they are charging at home, and when there's a flat, zero value, it means that they are not at home, they're not charging there, all right? And of course, these values go at 3.7, which is a level 1, and 7.4, which is a level 2. And you can see that there are many profiles. Those are just examples at the very left, because the idea here is just to show that there's a lot of diversity. And all of this is coming from these statistics from the UK Electric Nation project. Now, if you want to see how in the aggregate they behave, and then, well, you do the average, is what we see on the right. These are what we call diversified electric vehicle profiles. Now, these electric vehicle profiles, as diversified, from an average of more than 1,000 profiles, are divided into level 1, level 2, and weekdays and weekends. And what it already can tell you, if, for instance, for the solid lines that are the weekdays, is that, a level 2 that is originally, 7.4 kilowatts, because of the diversity, how people don't do things simultaneously, that value actually can be around 2 kilowatts. And during considering level 1, that value can be around 1 kilowatt. Now, those values don't seem like a lot, all right? However, the moment that you multiply this by the thousands, it can be significant, and it can be a significant added load to certain parts of the network that were designed with much smaller ADMDs, as I was explaining earlier. Now, something very important as well that is worth mentioning. We are aware that electric vehicle charging behavior is evolving, all right? So we are aware of, the links are there for you, of, for instance, a recent report from New Zealand, from Vector, another distribution company, that they are showing much smaller diversified values of electric vehicles. And also here in Australia, Ergon and Energetics, they released a report as well, where they were showing initial insights, and as well, the behavior was showing much smaller diversified demand. So it is important to bear in mind that these values can actually be smaller. At the same time, we are aware as well from other data sets, that actually these values are matching what it is being seen in certain parts of Australia. So I guess that the first recommendation here is don't take all the results that we're going to present as the definitive, but distribution companies and anyone that is interested, in this type of analysis, they need to update, these profiles according to the data that is available regionally. Okay, let's move on. So let's get into the impacts, and then let's get, of course, into the more interesting part, which is the management. Okay, we will have problems, challenges, sure. Can we address them? We're going to spend a little bit more time on that part, but I need to tell you, first the first part of the story. So in this case, now at this moment in time, I will pass on the word to Will. Will, are you there?
Yes, Nando, thank you. So as Nando said, we're looking at the effects that EVs are going to have on our distribution networks. If we look at purely the increase in peak demand, so we take the peak demand at any time of day and compare that with the peak demand when we consider EVs, we of course see quite a significant increase in that peak power. The exact increase in peak power will vary region to region, depending on existing loading, time of loading, proportion of residential demand to non-residential demand. All those things will impact the sort of exported impact upstream from the peak power. But nevertheless, we're looking at sort of a 25 to up to 100% increase in peak power, again, depending on all those characteristics. And that can be very significant for those assets upstream. So if we move to the next slide, please. So when we're talking about hosting capacity, as we mentioned earlier, that it's all about, are the assets within limits? Are the voltages okay? So here's an example of rural New South Wales with the LV distribution transformers. And we see that once we hit 20% and beyond, we start getting issues. So we can say, okay, 20% when we talk about the LV distribution transformers is the hosting capacity for this feeder, 40, 60, 80. We start getting some transformers overloaded, not all of them. and that ultimately limits the hosting capacity for the whole HV feeder. Yes, there's capacity on other transformers, but if we take the whole HV feeder as a whole, that is the bottleneck. So if we move on to the next slide, we can now see that we're looking at the residential customer voltages for the same feeder. Okay. Now here the voltages perform better than, say, the asset utilization for the LV transformer. And if we purely look at voltages, we can go up to 40% before we start getting some issues for some customers, not all customers. However, if you had to pick, okay, what's the hosting capacity for this HV feeder, you're first going to be limited by those transformers, which need to be solved before you then move on to, say, the next problem. So despite, we get issues at 60%, the hosting capacity is still 20% because we're limited by some problematic assets. Those problematic assets need to be resolved for those problems to be resolved, essentially. So if we move on to the next slide, please. The same story now appears with the LV conductors. LV conductors, we can host even more without problems, but those other problems need to be solved if we want to achieve higher hosting capacities. And finally, if we look at the HV feeder utilization, we can go every house with an EV for this feeder without causing HV conductor issues. You want to get there, you have to solve voltages, LV conductors, and LV transformers. So ultimately, there will be a bottleneck for every feeder. That is what is the problem you encounter first. That will vary feeder to feeder, region to region. And in this case, we hit our first bottleneck at 20%, which is the LV transformers. So if we move to the next slide, please. We can see this now clearly when we look at the summary. So we've got the transformers on the left, the conductors, the percentage of customers with voltage issues, and the length of HV feeder congestion. So we can see very clearly that, yes, we need to, for this feeder, we need to tackle distribution transformers to unlock that higher ability to host more EVs. So ultimately, it's all about what are the problematic assets and what limits your hosting capacity. So we move to the next slide. Yeah, so this is now a summary across the rest of the feeders. And we can see that it really does vary region to region. So urban New South Wales, we can go up to 80%, it's nearly every customer with an EV. Whereas, say, the Victorian feeders, they have real congestion problems that need to be solved. But you could, if you are able to manage those issues, you could get higher and higher. So, between sort of 20 to 80% is the sort of typical range we're finding as unmanaged EV hosting capacities for our networks.
One comment I just wanted to make. So we include here the Victorian voltage limits, the new ones, but these are limits that only apply when really things are going really bad. Okay, so in general, across Australia, the normal limits are plus 10% and minus 6%. But just for completeness with the slightly new rules, we created the voltage limits for Victoria as well. But if we really look at what they need to do, which is keeping it, between the plus 10% and minus 6%, of course, for the cases of the rural and urban Victoria limits, they might actually hit those problems much, much earlier. So you want to do the key remarks, Will?
Yeah. So in general, EV impacts are going to vary depending on the type of network and the residual demand. So if you have a higher ADMD, you can handle higher EV penetrations typically because your networks are built for it, but that can also bite you a little bit because you may have already higher existing load. So it's not quite as simple as that. It can work both ways, but in general, it will vary on your network and type of demand. Typically, we found rural networks can handle up to 40%, some lower, but up to 40% was the upper bound there before we start getting into issues. And urban grids could go up to 80% before we start getting into issues. Typically, it's urban feeders asset congestion is probably the main issue, whereas rural feeders, yes, asset congestion is also an issue, but voltages become a bit more of a concern in those rural feeders as we've got longer lines, longer the issues with impedances and voltage drops and that side of things. But yeah, in general, asset congestion is the predominantly limiting factor. So yeah, I'll hand it back to you, Nando.
So in conclusion, numerically speaking, yes, we have some challenges that can appear very quickly and depends on the network. So what can we do, to really increase the hosting capacity of those networks? So we have different alternatives, of course. We can do things with existing assets. For instance, our low voltage transformers, they have own load changers in many cases. So if it comes to to voltage issues, we could actually have better settings. We have been doing this, for photovoltaics. The challenge, however, with on-load tap changers is that if you have photovoltaics, then you were actually putting the taps down so as to have lower voltages, but now you want to bring the taps up for electric vehicles. You cannot do that simultaneously with an off-load tap changer because it's off-load, it's fixed, right? So we have some challenges there. Now, if you look at the off-load tap changer at the zone substation, then of course, there are a lot of opportunities that they can still, control and regulate the voltages properly for situations of photovoltaics, but also at night, for electric vehicles. So it can be used, but that is just voltage. And as Will was mentioning, and our results are informing us, there's a lot of challenges with asset congestion. So whatever you do with voltage is great, but that is not the only problem. And actually, as a matter of fact, the first problem will be asset congestion. What can you do? Well, replace your assets. Sure, you can reinforce them or augment them, as also it is known. So larger conductors and larger transformers. That is quite expensive and also time consuming, but it is an option. We can actually do voltage regulation with new type of transformers, such as on-load tap changers, but in the distribution transformers. Expensive to replace as well, of course, like for like, but it's an option. Or we could potentially as well, directly or indirectly manage electric vehicles. All right, so the idea here is to show that, well, different options will have different capabilities. As I mentioned, existing assets might help us with management of voltages, but not necessarily asset congestion. Then we have, the reinforcement that not much will help, with voltages, but certainly, with asset congestion can help, but they are very, very expensive. Now, if you actually look at new devices such as the distribution transformer or on-load changer, again, managing voltages would be great, but asset congestion is not going to be sorted out. So therefore, perhaps, from a cost-effective perspective, it is the direct or indirect management of electric vehicles that might be the solution or part of the solution, right? So it might be a good option, but to what extent? Because it sounds good at first, but we need to quantify this. And also what happens with electric vehicle users. So we need to quantify what might be the effects on them, if there are going to be delays on their charging, et cetera, et cetera. So let's discuss this a little bit more. Now, when we talk about direct or indirect EV management, what we're really saying is that, well, we are able to remove that load that was excessive and was creating challenges, so we can avoid those problems in the network. Now, what can we do then about it? If we're talking about direct management, it can be a distribution company, a DSP, distribution network service provider for our international attendees, or any third party. It can be an aggregator, for instance. They could disconnect the charging points, all right, when it is needed. You can do throttling as well, or scheduling the charging. That can be a direct form of management. And indirect management can be actually the use of time of use tariff, right? So we are going to explore the particular disconnection of charging points and time of use tariff in the next slides. So let's start with electric vehicle management. The principles of this electric vehicle management strategy that we are going to show, they started in another project called My Electric Avenue in the UK that we were just involved as well at that time. And but the application here, goes into the assessment of multiple distribution networks, the low voltage networks connected to the same high voltage feeder. So it's quite interesting here to see how it performs. So the principle of the management strategy is relatively simple. You just disconnect when you have problems, all right? So the philosophy is simple to understand. Now, of course, there are challenges because first, you need to know what has been connected. And that means you require an infrastructure that allows you to know that a car has been connected to the charging point and it is charging. So connection doesn't mean that it's charging, because if it is a full battery, well, it is not drawing any power, right? So we need to know that it's actually charging. So you will need an information, sent from that charging point to a central, entity, your scale, your control room, whatever it is. And this is needed from all the different charging points. Now, you also need to know more or less, what is also the feeder that you are connected to, because you want to know how that particular feeder, the low voltage feeder or low voltage circuit, will have some challenges in terms of congestion, particularly at the connection of the transformer. So really at the very head, because of the aggregated effect of all the load. Now, also, you want this monitoring to be in all the corresponding low voltage feeders, so you can actually assess in the aggregate what is happening with your transformer. Now, also from these charging points, you want to know, if possible, what is the voltage at that point, so you can assess where the voltage is too low. Now, of course, that can actually be supported by data if you have, smart meters. But if you don't have, well, even just with the charging points should be enough. Now, and all of this data, of course, goes through a central controller, if you want, and then makes decisions on what to disconnect. Now, how do you decide what to disconnect, of course, and what to reconnect? It has to have an intelligent logic, right? And that logic has to be intelligent in the sense that it makes sense and is, of course, practical at the same time. So what we were using here was simply the fact that when with our sensors, all through models, of course, we're having or we're noticing, really low voltages or really high currents that were exceeding the ampacity of our circuits or the transformer, we were disconnecting the equivalent number of charging points that would bring everything back to a values that are okay. Now, that is not that complicated to calculate. All the details are in the report, of course, all the equations and things. But what it is important also is to decide which cars to disconnect. So that means that we need to keep track of who has connected and is charging and take the time so as to then remove those that the equivalent time is much larger, which means that the state of charge is much larger than others. Not necessarily true, but if you don't have a lot of information, that is enough. And then therefore you remove those cars that have been charging more. And then when you need to reconnect, when there's a space in the network, you will reconnect those that actually have been waiting for longer. And that will bring a little bit of fairness, if you want, in terms of the use of the infrastructure. Now, the idea, of course, is always to mitigate asset congestion and voltage drops. And as much as I mentioned in that you need all this data, well, it is relatively limited infrastructure and inputs. And in this case, we don't need network models, which is very important because, as I was mentioning earlier, that is one of the challenges that many distribution companies have, not just in Australia, but around the world. So if you can actually do something clever without the low voltage network models, why not? So just to summarize, what we do is first a check of the phases, the voltages, the conductor, the transformers. We do a check of the corresponding feeders in terms of voltages, conductors, and then we start disconnected in a hierarchical way, all right? So the moment that we see that there's a problem or we're close to get to a problem, we are going to disconnect as many charging points as we consider that is adequate. Same thing, the moment that we think that there is no problem, but there is a space, there's headroom, for capacity, to have more cars, and instead the voltages are okay as well, then we estimate how many reconnections can happen, from the queue of cars that have been recently disconnected. And with that, we quantify as well from a simulation perspective what will happen to those cars that have been managed, because eventually these cars are people that are waiting for their car to be fully charged, right? Or to be charged to supposedly what they wanted, not necessarily fully charged. Now, that quantification is very important because it will allow us not just to say, well, this strategy helps the networks, all good, but what happens with AV users? So that quantification is very important. So how does this look like at the moment that we start doing these simulations and the profiles, So what you see, in green is the management, in blue is the no EV management. So without EV management, what you can see is that with the red line and the transformer plot at the top is that we might exceed, the capacity of that transformer, as Will was explaining with the results that we presented. That means that if we apply EV management adequately, we are going to be able to reduce that load, okay, in the aggregate, so normal load plus the electric vehicles, and push the electric vehicles to later, all right? So we can actually still charge them, but it will be at a later time. That means that the profile of the electric vehicle will now be different because now you're charging later, and that creates, of course, a delay that I was explaining. Now, that delay is important to be quantified because we want to understand what are the effects on the users. All right, so let's get into some results. Will.
Thank you, Nando. Yeah, so as it's sort of intuitive, if we disconnect the problem, we're going to inevitably help solve the issue. So, without EV management, we get congestion problems, we get voltage issues. When we then consider, okay, what are the voltages only for the EV customers, by the way, that we measure, or are the sensors sensing that the assets are problematic? We can take actions, and we can take actions without necessarily having the models of the LV feeders. We just do it based on what we see, what we know the limits are. So I guess, you need to know the size of the assets, of course, but, you don't need a comprehensive model of the feeder. And ultimately, it's all about disconnecting that problem and then reconnecting them when we have capacity, with the hope that the charging impact is not too significant for those customers. And ultimately, we're going to see a reduction in that peak demand, at least for the residential portion of the feeders. So we move on to the next slide, please. So this is just an example. Feel free to look at the report to see everything further, but we can see that, yes, without management, we have issues. We've got voltage problems, we have asset congestion problems, the transformer going over the limit. When we consider EV management, we bring that down below the technical limits. We manage to manage our voltage issues, without any forecasting, and we largely solve those issues. Any slight overloads, you could arguably be within the cyclic ratings, because when these are the nameplate ratings, we're not considering the cyclic ratings. So those slight overshoots, you could argue, are still within the design specifications. So if we move to the next slide, please. So here, the impact to customers is, of course, quite important. So this is a different feeder now, rural Tasmania. And we can see that with the blue is the charging time without management, and in the green is the charging time with management. So we're accounting for delays to some customers from managing their EVs, but we don't actually manage all customer EVs because we don't need to solve the issue. So in this case, we actually only, for 100% EV penetration, I do believe this feeder was limited to 20%. So we could go from 20% to 100% for rural Tasmania by managing just 9% of customers for 100%. Obviously, for lower penetrations, that figure is lower, but to get to every house with every EV, under 10% for this feeder, you need to actively manage. And in terms of impacts, the majority see 2 to 3 times increase in charging time. There are some outliers that could be further tuned with a bit more development in the control algorithm and that type of thing. But in general, charging times are, that's fine, because if the EV is full by, say, 6, 7, 8 a.m., that's probably okay, right? So in general, for this feeder, the majority of customers only saw a fraction of an hour increase in their charging time. So most customers are not really impacted at all, and suddenly we can drastically increase that hosting capacity. So if we go to the next slide, please, we should be able to see a summary. So what we can see here in this summary is a percentage of customers that were managed, percentage of customers that were unaffected, and then the sort of 75th percentile increase in charging time for all the customers, with or without management. And the takeaway here is between if we're considering every house with an EV, right at the end of the scale, the maximum we're going to impact customers is between 21 to 38%. Now, 38% is a really tough feeder to manage. That's probably the very hardest feeder you could really conjure up for that 38% figure. 21% figure is probably the next hardest feeder to manage to get every house with the EV. And then say, urban New South Wales, rural Tasmania, urban Victoria, and urban Tasmania, much lower. We're talking, around 10% and lower for customers, in urban New South Wales, less than 1% of customers you need to manage. So, you can manage these feeders without a drastic impact on customers. Yes, you might have a problematic feeder here or there where you may need a bit of reinforcement to bring those delays to more reasonable levels. But, in general, the impact to customers is not too severe, considering this is at night time and they're not using the EV. So if we move to the next slide, please. So, some key remarks here. So technically, EV management can mitigate congestion and voltage issues. You can do this in theory without a physical model running power flows. If you have sensors at the head of the feeder that can measure both the current in the conductor, because it's at the head of the feeder for each feeder, and that's where the problem is, at the head of the feeder. You can also figure out the transformer issues, and you have voltage information from those customers that you're managing. You don't need every customer voltage, only the EV customers. That's enough. You're able to perform this control, and that's quite significant, because getting models of LV feeders is tough. It's expensive. It's not common. Yes, some DNSVs have it, but not many. And ultimately, EV management is able to dramatically increase the EV hosting capacity without too significant impact on customers. Typically, less than 20% of customers need to be managed. You do have those outliers, and those that are managed, the impacts, 1.5, maybe up to 3 times increase in charging time, depending on how long you're charging for. Before management, most of that occurs at night. So yes, you're able to manage EVs with quite a limited infrastructure, and you don't necessarily need state of charge. This is all done without state of charge. You just need to know when the time they're plugged in and are they charging. So back to you, Nanda.
Well, so we are going to reflect on these key remarks later, in the final conclusions as recommendations, of course. But again, the message is, can we manage electric vehicles with some clever strategies? The answer is yes. Of course, there's an extra infrastructure that is needed, the communications, etc. But we cannot forget that we are affecting electric vehicle users ourselves. That eventually we'll have all electric vehicles. Now, this effect, as it is quantifiable, can sometimes be perceived as significant. But as Will said, and I'm repeating it because it's important, this charging is happening at night. So for many, many people, if not most people, it will not make a difference because they will be sleeping anyways. So that is an important consideration. Yes, when you read the report and you start looking at the different, extra hours that actually the management can create, in terms of charging, sometimes can look significant in some, edge cases that we call it, like the fringe cases, statistically speaking. But again, the context is we are looking at customers that normally will be, charging their vehicles at night when they are not really using it. There's no plan to use it. So there are significant opportunities in terms of EV management here. Now, let's move on to time of use tariff. Now, something very important here that I want to make it clear. Now, in this project, we didn't set ourselves to really find the tariff that will make people, able to be persuaded, to certain times of the day. That's not what we are doing, because that is a whole different type of research. So what we were trying to explore is, what if we define the hours that somehow we're going to find the prices, all right, at a later stage, that will persuade people to move, their charging to those times? Fine, but the big question is, okay, so how many people do I need to be persuaded to move their charging to other times to really see significant benefits also for the poles and wires, right? So that's what we investigated. And what we used wasn't really tariff per se, but tariff profiles. So let me explain that in a little bit more detail in the next slides. So first of all, why should we use time of use tariff? Well, first of all, because it's relatively simple, right? Of course, if enough people do change their behavior accordingly, all right, we wouldn't require much more infrastructure. I mean, something that to many extents we are already used to across Australia, and it can be combined with different other solutions, anyways. So it is not necessarily the silver bullet, but actually, if this is combined with other solutions, well, why not? Now, as I mentioned, what we did was a sensitivity analysis, right? So we defined times to encourage EV charging, all right? And this is what we call the time of use tariff profiles. It's a proxy of, of what would be, a high or a low price. Now, we define different adoption rates. So if 20% of the people are persuaded to really change their behavior, what will happen to the network? And then 40%, 60%, et cetera, et cetera. That's the idea of the sensitivity analysis. And then we quantify, how much demand has been shifted, and we run the corresponding simulations, all these three-phase power flows, these beautiful things of this detailed analysis, and then we see what happens. Now, what you're going to see, of course, is something very interesting, because a time of use, I mean, kind of like a spoiler alert here, the moment that you set a time of use tariff, and in our case, a profile, you set a block of hours where you are actually persuading people not to charge or to charge, right? In our case, we are going to persuade not to charge, which means they will be charging at another time, at a later time, most of the time. But because of the nature of blocks of hours, that you are dissuading people to charge, then it means that they will charge immediately after. That immediately after will create what we are going to call in the next slides a second peak. So whenever you hear a second peak, what we mean is this effect where everyone now starts charging when the prices are much lower, and then therefore, everyone is charging, and then there's a very, very high coincidence. A high coincidence is what really creates significant challenges for the networks, because this is just a big spike of demand that then the networks need to deal with. And we're going to go a little bit deeper on this. So let me just graphically show you what we are expecting, from the use of time of use tariff in general, in the context of this project time of use tariff profiles. So once you set a profile, right? So for instance, what you're seeing there in blue is with the time of use tariff, so supposedly will be more expensive from 5 p.m. to midnight, all right? And then at other times will be just cheaper. So the idea is, to persuade people to charge at other times when it's cheaper. Now that means that, the green profile in the middle, that is the EV charging without time of use tariff, will actually change, and it will change towards the times that are cheaper, right? And that means that, of course, that profile of the charging of the electric vehicle will be modified. So that's what we did. We were modifying it according to the profiles. So this EV charging will occur now outside the normal peak, which is fantastic, right? That's a happy face there. But the point that I'm trying to make with my comments earlier is that happy face for the peak time, but we might create a second peak later on. We're going to demonstrate that. So if we look at the periods that we need to select, well, we need also to be careful with the timing of that period with respect to the region that we're talking about. So it's not that, we can simply say just as a blanket policy, well, 6 p.m. to 8 p.m. will work for all the networks, because the regions are different and then the demand is going to be different. So we need to reflect on that. So what we did is, for each of the different networks that we actually were modeling, we looked at the actual peak hours that they had, and we used them, to define the profile and the hours that would be, discouraged, for the electric vehicles to charge. Now, these hours are 5 to 9 p.m. for the urban TASI networks and the urban Victorian networks, and 6 to 10 p.m. for the other three networks, the rural New South Wales, urban New South Wales, and rural TASI. So this analysis was done with these different times, and more details, of course, in the corresponding report. So let's start seeing the results. Will.
Thank you, Nando. Yeah. So what we're showing here now is a sort of snapshot in time, if you like. So we're looking at a 24-hour period, but we're looking at one feeder, rural Tasmania. We're looking at one type of asset here, the LV transformer utilization, and we're looking at just one EV penetration, 60%. What we're showing here in these 6 plots are the different uptakes of time of use. So because we're not focusing on the cost required to move demand, we're not considering price elasticity. It's more of a sort of sensitivity analysis saying, okay, if we got 20% of our customers to move their demand, what's that going to look like? And what we can see is that, yes, immediately we move to 20%, we see a slight reduction in that peak, which we expect as some customers now start shifting their demand to later, 20% of them. 40% is really where it starts to deviate. So yes, we get a larger headroom, but now we're starting to eat into that diversity that was there in the native use of profiles. When we start assuming, okay, 40% of customers are now going to charge within this window, 100% of those 40% are all going to start charging at the same time, pretty much. So that really loss of diversification really can be a big challenge for time of use. And then we start seeing this second peak, from 40% depends on the nature, but generally 60% and beyond, you really start getting second peak issues, and some cases 40% and beyond, some cases 40% is okay. But the key here is that, yes, when you start eating into that diversity, you're going to get issues, and there are ways around that. We see that, for instance, in time of use tariffs for pool timers that are common in Australia, that if you stagger the time of use, maybe you can mitigate that effect. But unless you're staggering it over the exact same window that you moved from, you're still going to have some diversification problems, and you're still going to get a second peak issue, maybe not quite as severe, but it's definitely something to consider when you're getting such high uptakes. Now, are you ever going to get such a high uptake with a tariff? Because we know typically that demand is not that elastic. Then again, EV demand is perhaps easier to use, and we'll get into that into the recommendations. So if we move to the next slide, please. So yeah, if we now look at the net demand comparison here, so this is if we take the power right at the head of the HV feeder across, hundreds of customers or thousands of customers, depending on the feeder, yes, we see a reduction in our peak demand when we consider time of use. And then when we start going beyond certain penetrations, the loss of diversification causes a higher peak than we initially had, and we actually get a worse problem than we did. So there's definitely they definitely help, but there will be a limit of where you then start running into problems, and that needs to be considered. So if we move to the next slide. So this is just a summary of 4 of the feeders. There's not room for the Victorian one, so do check the report if you want to find out more. But yes, we typically see an increase of about 40%, of about 20% increase in hosting capacity with time of use when you pick an appropriately sized adoption rate. However, beyond that, we start getting issues. So if we move to the next slide, please. So yeah, time of use adoption rate, you can get 20 to 40% seems to be the sweet spot. Usually 20% seems to be the most performing, 40% pushes it. Some cases you can get slight, second peak can be an issue. Sometimes it's not, but that reduction can be significant enough where the second peak isn't quite a big problem and you're right at the limit. Certainly beyond 40%, you really do start getting problems. Yes, it does lower the impact. Some cases, some feeders, you increase the host. If you have a 20% adoption rate or 40% adoption rate, you will still have issues. It won't solve everything in the network. In these cases, you're still helping the network, but you're not solving all the issues to enable higher hosting capacity. So in these instances, if we're considering a realistic scenario where we're considering complete solutions where you're still going to reinforce the network somewhat, time of use may reduce the amount that you need to reinforce the network because you're lowering the peak utilization of assets, even though you're not completely solving the issue. And that means you may need to replace few assets and so on and so forth. And finally, second peak can be significant, and it's all about diversification. If you remove that diversification and everyone all charges at the same time, you're going to have an issue. So if you start getting really high uptakes of these kind of tariffs, measures really need to be thought about, okay, how do we reapply that diversification to avoid this issue? Thank you. Back to you, Nando.
All right, so just to finalize this presentation, I know this is super short, there's a lot to talk about, much more details in the reports, of course, but let's go to some high-level recommendations from this assessment that we have done. So from the perspective of electric vehicle management, I think that the strategies that manage electric vehicles without the requirements of hardcore power flows, if you want, or even simplified power flows, is the way to go, because it will facilitate just focusing on the other parts of infrastructure that is needed, to really gain those set points or data that you need, to understand, what to disconnect, etc., etc. So all of that already is not necessarily cheap and not necessarily simple, but if on top of that you need the low voltage model, then it really creates many, many challenges for most DNSPs. So a strategy that doesn't require the network, that is network agnostic, is always welcome. Now, what we have seen, as much as we were talking about electric vehicle management as pushing the customers to charge later, what we have seen is that the large number of customers have very, very little impact or no impact whatsoever. But still, we cannot forget that there will be some customers that are going to be impacted. And if there are ways of sort of compensating them, or perhaps investing efforts in those small transformers that we see that are the most challenging ones, perhaps that is a solution where you have electric vehicle management, but you know that there are certain spots, that you can actually just do your traditional augmentation to benefit those customers, but the large majority are going to be okay with just the normal electric vehicle management. Now, there are improvements to do to the electric vehicle management in terms of timings, control cycles, and different things. We have much more details in the report, of course. So it's not that we are saying that this is the perfect strategy, right? Now, something that is very important as well, that any electric vehicle management strategy, as much as possible, should have minimal information as inputs, right? So you can make the whole infrastructure much simpler, and the whole passing of data as well much simpler to handle, as well also because of customer privacy. Now, moving on to time of use tariff profiles. So of course, the idea is to really find that the tariffs that do encourage, this change in behavior. We haven't really discussed the actual prices. Of course, that's another piece of work. And we are not even experts on that, actually, as a matter of fact. But it definitely shows that, if we start really having certain adoptions, even as relatively small adoptions, as Will was saying in our results, even with 20%, you can already find a shift that is significant for the network perspective. And that's great, right? Now, time of use tariff can reduce the cost of network augmentation. So it's something that can complement other solutions. We cannot think of, or we shouldn't think of electric vehicle management as a solution and time of use tariff profiles or time of use tariff as a separate solution. We can combine them, and then we can have the best of both worlds. So that's the takeaway from that point. Now, also, well, time of use tariff could be pushed as late as possible, and that can be actually very beneficial. And also focus on minimum demand. Now, when we say focusing on minimum demand, what we say is encourage minimum demand rather than always trying to move people away from the peak demand. Encourage, minimum demand, and naturally, people will actually move to those different hours. Now, Will was mentioning about the staggering of time of use tariff. That's very important. Of course, this is not news. Those of you that are aware of how electric water heaters are managed in different parts of the world, all right. And this is a staggered approach when you have a whole nation, so because you don't want this second peak to happen. That can happen, of course, and we know this already from other technologies. So it's not news, but of course, modeling it, showing it to you and to the different stakeholders is important, just to be aware that if we move to time of use tariff as one of the potential solutions or in combination with other solutions, we need to consider the staggering as well. Now, there are different challenges with time of use tariff profiles, because as much as distribution companies can actually set up tariff, it doesn't mean that it is reflected on the actual tariff that the suppliers, the energy suppliers, are going to give to the end customer. And that is a big challenge for distribution companies. So there has to be some communication between the energy supplier and also the distribution company to ensure that these tariffs are actually going to reflect or are going to really persuade customers to move away from certain hours, or persuade them to go to another hours for the benefit of the network. Now, finally, something that is very important, as much as time of use tariff can be very beneficial, as we were saying, we need to quantify somehow as well the low voltage feeders effects. So what we're saying is that, sometimes it might seem that, the whole peak is moving, towards other hours, and that's nice, but without quantifying what is happening in each of the distribution transformers, we might have some false conclusions. So this is just kind of a word of advice, for anyone that will continue this analysis, in particular for distribution companies. Well, with that, we finish actually this presentation. We have a few minutes, and I will be more than happy to go through some questions super quick. We will share these slides. The report is already live. We will share the links as well. There's many other links that we are going to share in these slides. But before we go into the questions, I just want to thank, of course, ENA, C4Net, API, OSNet Services, Energy Queensland, Endeavour Energy, Gemini, Power Core City Power, United Energy, PowerLink, TAS Networks, all our industry partners that were helping with feedback, with the data, etc. And of course, Jing as well, that is part of the university and was helping us with the different models of electric vehicles. All right, Will, so let's try to go through some questions. David, is it okay if I go through some questions?
Hi, Nando, absolutely. I'm just flagging. So we do have people heading off now. Obviously, they've
of course
other things,
absolutely.
but given that we're recording and there's been lots of great questions, I'd say, as a bit of time on questions would be great. So yeah.
All right, excellent. So let's do just a few minutes, because I don't want to bore to death people. But let's go through these questions. So I'm gonna go just super quick. I'm just seeing here a chat, videos. What is the increase in peak power that you are expecting when the diversified electric vehicles across the name? This is a question from Lawrence. Thanks for this question. So the diversified values that we presented, Lawrence, they were already for thousands of vehicles. So we don't expect significant changes. Now, again, be careful with the diversified profiles that we provide. So 7.4 kilowatts at level 2 became around 2 kilowatts, and the 3.7 around 1 kilowatt. Now, don't use that lightly, because in reality, as I was mentioning, from the results from Vector in New Zealand and as well as Ergon Energy Next, we are seeing as well in other regions other behaviors where actually the diversified peak is much smaller. And also something that they mentioned, not just smaller, but also happening later, which means it's not coincident with the peak demand necessarily. So that is very, very important to bear in mind. So we need more local data, and we need to, of course, consider the potential future behaviors. Just a couple of things, the data from Vector, they mention actually very clearly that people were already aware that if they charge later is good for the whole system, and some people were doing it. They were not pushed for that. And also they were saying that some of the electric vehicles as well, they come with default charging times that were much later, like 9-10 p.m. That automatically many people don't change the defaults, and then that was happening. So it was already a shift that was happening there, and that's why they saw lower peaks as well. Now, in the case of Ergon, if I remember well from the report that the brief report that they put together, as well, there were a lot of people that were using their batteries, and then they were charging during the day, or they were trying to charge mixing with the photovoltaic that they had. And then, of course, that naturally meant that they were charging much, much less as well at night. So we need to be aware of those considerations as well. Now, other question here. Thanks for the presentation. Oh, awesome. What do you mean by EV hosting capacity? Well, I already provided the definition there earlier. Anthony is asking that we need to look, or mentioning that we need to look at dynamic operating envelopes. Well, I mean, it might be the case, Anthony. Operating envelopes can help. It requires a different type of infrastructure, of course. But then the question is, who is gonna change the demand of electric vehicles according to the operating envelopes? And this is one of the challenges that we need to consider. Operating envelopes are very interesting, but when there's a third party, that is managing your devices at home, who is going to manage this electric vehicle? The idea of this electric vehicle management strategy that we were presenting is targeting the charging point. So therefore, that entity that is managing the charging point can actually do it. With operating envelopes, you still need someone that has to manage. And it's likely that it's not going to be us as receiving in our phones, what is your operating envelope for the next 24 hours? I'm not sure it's going to be like that. But anyways, that's just me. I think that we need aggregators or third-party companies that can take that action. How is it related with photovoltaics and renewables in terms of the hosting capacity? Well, in terms of hosting capacity, it's the same thing. It's how you define it, but I already provided the definitions, Jim. Keegan is asking, when disconnecting electric vehicles to manage voltages, what devices need to be present at the customer premises? Just the charging point, because the charging point is also can measure the voltages. Are these devices already present, or do they need to be installed by a aggregator service provider? No, this is the normal charging point, but it's a charging point that has to have smarts. And that smarts that I'm talking about should be the ability to communicate to this control center or the aggregator that will receive a signal to disconnect the charging point, all right? So it's not just a normal charging point that has to have the ability of communications, and this is actually happening already anyways. Gabriel is asking on slide 34, I don't know which one.
So that's the the number of hours, that's the upper quartile. So it's the sort of upper average, if you like.
All right, so you want to answer that one?
Yeah. So it's saying we have a slide with the EV management impacts with hours, and those hours are the upper 75th percentile. So it is an average, but it's a sort of a higher average, trying to push as high as we can without then incorporating the edge cases, which could be improved upon as you develop EV management. So it'd be a bit silly to take just those edge cases, but we still discuss them in the report.
Excellent, thanks, Will. Alex is asking, what is the average number of customers connected per feeder in the study? Would this affect the mitigation method? Actually, we have an extremely diverse.
I've got some numbers. Yeah, so lowest numbers is about 620 for urban New South Wales and urban Tasmania. The rural Tasmania and rural New South Wales are about 1,500 customers, and then the Victorian feeders are much larger. They're about 3,500 customers. That's residential. That's total customers. Yeah, but mostly residential. But then you get commercial that are much larger. I won't get into it.
So very, very diverse, Alex. I mean, as diverse as the networks are, actually, as a matter of fact. Catherine is asking, was the style of charging where you set your vehicle to finish charging at your start of the day considered? Yes. This is all coming from real data from the UK Electric Nation project, and it covers the whole day. So yeah, it covers the whole day. Now, you're mentioning as well in your second part of the question, some of the cars recommend discharging as it is better for the batteries. Well, yeah, I mean, again, what we are not forcing a model of electric vehicle demand. We are just using real data of actual users from the UK. And yeah, that's what it is. Now, Keith is asking, how can we access the report? They refer to, oh, there's a link. We will provide that to David. I mean, when they send, he sends a message to everyone, just releasing the videos as well. We will be sure that we will provide that link as well to the report. But you can also take a look at our websites of the project. Well, at least next week, because we need to update them, of course. Thank you. Peter is asking, rather than delaying charging until 22 hours at 10 p.m., have you tried time of use charges to delay charging until early hours of the morning?
That was actually one of our recommendations.
Yes, actually, that's true. Go on, Will.
Yeah, so absolutely. Based on what we've done, ideally, if you were to start again, you would design the time of use around minimum demand rather than pushing away from peak demand. So try and encourage uptake during those really low demand periods. Then that second peak issue is going to have a higher headroom. And if you stagger it, even better, right? So if you can just push the time of use as late as possible and then combine it with staggering, yes, I think early morning you could get slightly better results with time of use, certainly. But then you run into issues of, will it be charged in the morning, right? So I wouldn't go much past 2 a.m. because, you know, some customers 4, 5, 6 hours. Some are much lower, but some do need quite a few hours to charge.
Okay, and this relates as well to the question from Peter that is asking about the second peak and the possibility of a customer accepting a small random time delay depending on their charging time. Yes, that can happen as well, but perhaps, you know, if you are applying the time of use tariff, then perhaps the staggering strategy is what really is more adequate. Now, how much can you stagger within the same feeder, you know, within the same distribution area? That is a little bit complicated as well, because what you want is to have a standard, you know, price profile, you know, for all your customers in your region. So it gets a little bit tricky. But at least if we look at, you know, the potential issues that might happen at the sub-transmission and transmission network, the staggering might be much more realistic as well. But yeah, I agree, Peter. Perhaps, you know, some delays in how actually they come back, you know, that can be implemented in the EV management strategy as well. Although the second peak doesn't happen with the EV management strategy, just with time of use tariff. Now, there's a question here from Harry. Have you seen any schemes or research on using discharging of electric vehicle battery? Where do you, yeah, that's called vehicle to grid. We're actually doing some research. Hopefully we'll send some interesting reports in the near future. However, there is a project, there are at least one project that is funded by Arena that is already investigating vehicle to grid. So I encourage you to just, you know, Google it. I forgot the name of that project. But in this case, we did not consider anything with vehicle to grid. Mohammed has mentioned a standard, how we want to say the load for visual units power management system. Yeah, I'm really not familiar with the standard, Mohammed, so I cannot really provide any comments. Ian is asking the acceleration of smart meters required for time of use tariff consumers. Well, I mean, I don't know. I mean, I don't think that time of use tariff, as we presented it, requires, you know, a smart, but it does require smart meters, or an
interval meter, yeah.
Yeah, or it might require an interval meter. You know, they don't need to be super smart. We already have time of use tariff profiles in different parts of Australia, by the way, and without necessarily smart meters. But you need just certain level of smartness, you know, just to control that the corresponding time as well. You can have separate meters. So, for instance, in the UK, it's very common, you know, to have what they call the I forgot the name. Well, do you remember? The separate, the cheap, the economy meter that is already, you know, creating two circuits where you have your
economy 7.
Economy 7. So that is nothing smart. You have a separate meter that actually just connects the load that is actually being managed as well. You know, that only, you know, you supply power when there are specific hours. So there are many ways of implementing this, but of course, with smart meters would be much easier. Yeah. Lawrence is mentioning, you know, a couple of things about the lessons, you know, from the industry with the standards, reduce power with the voltages. Well, this is a little bit more complex, Lawrence, when it comes to electric vehicles, because their ability to react to voltages is something that has not been considered so far, and we need to be very cautious as well, because it is not it's not an static load, first of all, and second, it wouldn't be necessarily electric vehicle, it would be the charging point, and that might increase the expense as well of the charging point. Now, is it possible to think of a charging point that actually manage the charging according to the corresponding voltage? Well, it might be possible, but technically speaking, and based on what we are presenting in our reports, voltages might be an issue, but the first thing is your assets. All right, and this is really the real issue, is your assets. So you need to manage all this demand as power, and voltages. The moment that you manage the issues with assets, which means you have to have lower demand if you manage it. Then of course the voltage problems are going to go away. So when it comes to electric vehicles, the first problem really in most cases are the asset congestion more than voltages.
If I could just add on there, we have a similar question in the Q&A that says, rather than EV management required comms, could we use volt var? And it's exactly the same answer, except that if you, yes, voltages, it will help. Voltages are not the main issue. And if you want to manage for asset congestion, you need to ultimately probably manage those assets and then relay that information, and that will require a small level of communication, certainly.
Thank you. So now talking about communications, Neil and Scarlett are asking, the information, the communication required for EV management. So the communications, it can be whatever works, for the corresponding distribution company, but you need to extract the corresponding information that the car is charging at home. So the charging point can give you that information, but you need, a charging point that is smart enough to send that through whatever it is, the communications that you are using. It can be the same communications of what we use here in Victoria, for instance, for the smart meters, can be hardwired, can be whatever it is, going to the cloud, through different ways. So that is something to be sorted out. And of course, it has to be done in the most cost-effective way. But in terms of the actual information, Scarlett, that we just require from electric vehicle customers, nothing really. We just need to know what the charging is doing, the charger, as in the car is charging or not. But the idea of this strategy is that really requires very little information from the customers. And of course, the moment that you know that you have, the comms with the charger, you will know whether it's a charger that is supplying 3.4 kilowatts or 3.7 or 7.4 kilowatts as well. So the information is important, but that's information that is fixed, unless you just change the charger. But no, you don't need anything else for the management. That's the beauty of that strategy. Well, more details, of course, in the report, but you don't need any information from the EV users, just the charger and knowing when they connect. What sort of incentive is needed to get the electric vehicle owner to participate in EV management? Neil, that's a very good question. We haven't answered that with our report, but however, I do encourage you to take a look at the reports from Patricia. So these are the first reports that we have done in this project. So they include customer surveys that will allow you to really not know what incentive will help, but at least see the willingness of customers, to be managed. And actually, we were very surprised that actually people might be very willing, to have the electric vehicles managed by a third party. Of course, with some caveats. Fair enough, but actually the willingness is quite high. So I encourage you to take a look at the report that is already publicly available already for some time. All right. So
a few more questions in the Q&A that I'd really like to just get to. Stephen Lowe asks, any comment on workplace charging during the day? We don't model that, but that would absolutely help. Any charging that you don't do at home, which is what we're modeling, will benefit. The extent to which that helps is yet to be seen. And obviously workplaces will have their own distribution networks, right? But it will help because you're diversifying further. There's another question.
But if I mention something, still thanks for that question. But definitely, workplaces we're going to have multiple charging spots, the charging devices, and in those cases, what we need is a local management system. That's it. So there can be a consideration of a local management system that is managing, like multiple chargers there, and in the basement of the building. Caltech is doing that already, and but that perhaps might need to coordinate as well with other activities that to have a whole distribution network that is managed accordingly as well. So there could be some coordination opportunities there with this EV management strategy of all the residential cars and also, parking spots, etc., etc. So I think that there are opportunities there, but when it comes to big customers that have their own parking spaces, they need to manage themselves. That's it. So there will have to be some coordination on the list.
There's a question here: will a community battery help? It will help the HV feeder. You're still, depending on where the battery is, if the battery's at the head of the feeder, you're still going to get congestion problems in the conductors. You might be able to solve the congestion problems at the LV transformer. And you might still get voltage issues, but it will help, but it's not going to solve everything, because you still have, all depends where that battery is basically.
Excellent. So going through the Q&A, I noticed as well there are some questions at the very beginning. So I'm going to go super quick and then we're going to finish there, guys. Just not to exceed the times here so much. Do you have any data compared to EV adoption projections so that we can understand what is likely to recover? No, we don't. The projections were done by, we didn't use projections here. We used just different penetrations, but projections such as the one that I presented very early in my slides, they are available on the EMO website, on the report. But projections are projections. They are never right? Peter is asking, well, a community battery, why did you answer that? Will, thank you. Ali is asking, how can we convince EV owners? Well, I mean, yes, as I mentioned, we didn't look at, how to really convince them, but I would encourage you to look at the report from Patricia, the customer service. There is a lot of willingness as well, but of course we need to learn what is the right price. If we go for time of use tariffs, what is the right price? But also with the time of use tariffs, I really want to highlight the fact that as much as distribution companies could come up with a very good strategy there, if there's no coordination with energy suppliers, here in Australia, these are separate entities. In other countries, they are the same, but here in Australia, separate entities, in Europe as well. So if there's no coordination between the distribution company and their profiles, the tariff profiles, and the energy supplier, then we are not going to see any results. So those profiles, those tariffs need to be reflected on what the energy suppliers do. Now, the problem is that energy suppliers might not like it because might not have enough appeal, for customers to sign up. Right? So that is another issue. But I just wanted to mention it because it's important to discuss it. There's another question from Anonymous there. Right, if you managed.
We answered that one. Yeah, we answered that one.
Good stuff.
But by the way, just on that last question, cost reflective tariffs could help with this incentive. So if there's tariff reform and tariffs are based on your contribution to the peak cost effect, and this is already discussed in reports and commissions, then if you're starting to pay towards your peak demand, then there would be an incentive. But that's for the next report.
Yeah, I'm just aware of time, so we are 20 minutes beyond what we was scheduled. So unfortunately, I won't be able to go to the rest of the questions. Thank you very much for your participation. I do encourage you to go through the report and the different webinars if you're interested. Thank you very much, Will, as well, ENA, API, and C4Net. And that's where we stop. Thank you very much.
Thank you, guys. Thank you.